Moving forward, let's talk about necessary and sufficient conditions a little bit more. So I'll remind you that two classes are equivalent if they have the same members. The combination of property restrictions on a class and class equivalents enables expression of necessary and sufficient conditions. So in other words, this is how we're going to do necessary and sufficient condition expression in OWL. So for example, suppose that we say for all x such that man of x if and only if person of x and gender of x male. This necessary and sufficient condition expressed in predicate logic with universal quantification. We can express exactly the same concept in controlled English by saying a person is a man if and only if gender always has value male. So what we've said is a person is a man if and only if, and the other part we haven't covered is gender always has value male. So just a note here on this if and only if. Logicians say if and only if, but the saddle grammar allows this to be shortened to only if you wish. So if you don't have any logicians nearby, you can shorten it without probably too much complaint. So just as a clarification, a reminder, what this means is if we know that John is a person with gender male, that implies that John is a man. Or on the other hand, if we know that John is a man, then that implies that John is a person with gender male. As another example, consider this predicate logic expression. For all x, parent of x, if and only if person of x and there exists some y such that person of y has person of y and child xy. So we can say this in our controlled English. We can say a person is a parent only if, remember that that's short for if and only if, child has at least one value of type person. So a person is the x in our universal quantification, is a parent. So that is saying that this condition is met, is a parent if and only if child has at least one value of type person. So we've already got this person who is x, and now we're saying there exists some person y that's a child of x. So what this means, again, is if we know that Mary is a person with child John, then that implies that Mary is a parent. If we know that Mary is a parent, then that implies that Mary is a person with child, a person. If we only know that Mary is a parent, we obviously can't from that infer the name of her child. We can only infer that there exists a person who is her child. Subproperties. Just like classes, properties can be partially ordered into a hierarchy. This is expressed in OWL with the RDFS subproperty of relationship. And what it means is that all pairs related by the subproperty can be inferred to also be related by the superproperty. As an example, suppose we know that son is a type of child, or in other words, son is a subproperty of child. Then if we know that Benjamin Franklin has son William Franklin, that implies that Benjamin Franklin has child William Franklin. We can infer from a relationship with the subproperty that there is also that relationship with the superproperty. Let's talk for a minute about some special types of properties. A transitive property means that, for example, let's say that located in is a transitive property. If Atlanta is located in Georgia and Georgia is located in USA, then that implies that Atlanta is located in USA. That's what it means to be transitive. If we have has a transitive property B and B has a transitive property C, then A has a transitive property C. Symmetrical property. For example, suppose we know that spouse is symmetrical. Then if Tarzan has spouse Jane, that implies that Jane has spouse Tarzan, or vice versa. So symmetrical property says that the same relationship exists between an object and its subject as exists between the subject and the object. Functional property. A given subject can have only one value of the property. So suppose in controlled English we say that biological father has a single value, then that means that for any given subject there can only be one triple with that predicate. Inverse functional means that only one subject for a given value of the property. So is birth mother of has a single subject is an expression of inverse functional. So that means that if we have is birth mother of George, then there can only be one person, one instance who is the birth mother of George. Inverse properties are also interesting. If we say that owned by is the inverse of owns, then that means that if George Washington owns Mount Vernon, then we can infer that Mount Vernon is owned by George Washington. So inverse properties come in pairs, the property and its inverse. So whatever relationship of the property exists between subject and object exists by the inverse between object and subject. Question: can an AL data type property have an inverse property? And the answer to that question is no, because the value of an AL data type property is a data value, a number, a data string, any kind of a data type value. And a data type value cannot be a subject in AL. So therefore there cannot be an inverse property because that data property value cannot be the subject of another expression. So no, a data type property cannot have an inverse property. Let's revisit the definition of classes. There are two ways to define a class or a set. We can define it extensionally, meaning that the members of the set are enumerated. So an example of that would be season as a class can only be one of spring, summer, fall, winter. So we've said that this class season is exactly these four instances and nothing else. And in our controlled English, you can say is a class must be one of or can only be one of, those are equivalent in terms of their AL translation. And here's the XML representation of this AL model. We have the class season. It's equivalent to a class which is one of these four instances. So that's the first way to define a class extensionally. Obviously that has limited application. There are many classes or sets where there is no possibility that we can enumerate all of the members of the set. Imagine the set of trees, for example, in the world. One would be hard-pressed to enumerate them. So that brings us to the other way of defining a class, and that is intentionally. When we define a class intentionally, we specify the conditions of set membership, and then everything that meets those conditions can be inferred to be a member of that class. So how do we define the conditions of intentional set membership? Well, by establishing necessary and sufficient conditions on the class through axioms would be one approach. A second way of doing it is with an explicit if-then rule that concludes class membership based on a set of conditions, and we'll talk about that later. So two ways of defining conditional or defining the conditions of intentional set membership by necessary and sufficient conditions and by explicit rules. Let's compare just for a moment necessary conditions versus necessary and sufficient conditions. What properties members of a class should have constitute necessary conditions, and it's implemented as property restriction conditions on the class, and the class is a subclass of all of the things meeting those conditions. So necessary conditions, if you will, is, as we saw in propositional logic, gives us the conditions that are necessary, whereas necessary and sufficient conditions, when the conditions are met, it implies class membership. So class membership implies the conditions are met, conditions met implies class membership. And this is implemented in OWL with an OWL equivalent class relationship between the conditions and the class. So in other words, the class is an equivalent class to all of the things that are meeting the condition, meaning there's nothing that meets the condition that's not a member of the class. So with that said, let's delve into property restrictions on a class. There are four main types of property restrictions on a class: cardinality restrictions, some values from restrictions, all values from restrictions, and has value restrictions. Let's start with cardinality restrictions. Cardinality restrictions can be exact cardinality, which usually we just refer to as cardinality, and that says that any subject from the class has that number of values of the property. For example, spouse of person has exactly one value is stating a cardinality restriction on the spouse property on the class person. Minimum cardinality says that any subject from the class has at least that many values of the property. Might have more, but must have at least that many values. So for example, child of parent has at least one value. Child of parent might have more than one value, but can't have less than one value. Otherwise, the instance does not belong to the parent class. Maximum cardinality: any subject from the class has at most that many values of the property. So for example, loan of library patron has at most 50 values. So this is saying that the library patron cannot have a loan property with more than 50 values. There is a special kind of cardinality called qualified cardinality, and that specifies not only the number of values that an instance of the class can have, but it also does it for each type of value. Qualified cardinality actually comes from OWL 2. It's not a part of OWL 1, and it is a part of OWL 2 that is supported by our controlled English saddle environment and by our underlying third-party OWL implementation, RDF implementation using Jenna. So for example, digit of hand has exactly 4 values of type finger. Digit of hand has exactly 1 value of type thumb. This illustrates that we are saying how many values from each of these different classes. Pet of cat owner has at least 1 value of type cat. So a cat lover might have other pets that are not of type cat, but in order to be qualified to be a cat lover, they're expected to have at least 1 pet of type cat. Or loan of library patron has at most 10 values of type DVD. So maybe the cardinality restriction is 50, so the library patron can have 50 values of loan, but only 10 of those can be of type DVD. There are other property restrictions. Some values from: members of the restricted class must have 1 or more values of the property from the value class. So this is actually an expression of existential quantification in OWL. An example of this is pet of cat lover has at least 1 value of type cat. And you'll notice this is very similar to what we saw under qualified cardinality restrictions. We said at least one value of type cat, and that was qualified cardinality. Here we say at least one value of type cat, and it's a subtle difference, but the fact that we're using the word one means that we're using a some values from. If we used an actual numerical, a number, it would be a qualified cardinality. The legal implications are pretty similar, so it's not like they're completely different in meaning. It's just a difference in terms of what kind of structure is created within OWL. Now let's look at why this is existential quantification. So consider this predicate logic statement. For all x such that cat lover of x, or maybe I should say for all x, if cat lover of x, then there exists y such that y is a cat and x has pet y. Note here that this outer for all or this universal quantification, this is just doing a range over all members of the class cat lover. So that's not really what we're talking about when we say existential in this case. It's in the implication. The implication of this is that there exists some y, a member of the cat class, with this relationship. So this is the quantification that we're talking about when we say that some values from is existential quantification in OWL. Another type of property restriction on a class is the all values from property restriction. This means that members of the restricted class can only have values of the property from the value class. And note that it does not necessarily have any values. It doesn't mean that there have to be any values. It just says if there are any values, they have to come from the value class. This is an expression of universal quantification in OWL. Our controlled English representation would be, for example, loves of rich man only has values of type money. Looking at this now as a predicate logic statement, for all x, for all y, rich man of x and loves xy implies money of y. So once again, the first quantification is just over all of the members of the class. So for all x a member of rich man, if x loves y, then y must be money. And so the quantification that we're talking about here is the quantification over y in this expression. Universal quantification in OWL. And finally, another property restriction on a class is the has value restriction. In this case, members of the restricted class must have the specified value for the property. Every member of the class must have that specified value for that property. For example, gender of woman always has value female, is how we would say this in our controlled English. This brings us to our next exercise. So the task at hand here is to build a genealogy model that captures the following features. There is a class person. It has defined subclasses: man, woman, husband, wife, parent. There are properties in this model: parent, child, spouse, sibling, gender, age, date of birth. There are some restrictions beyond what is sort of implicit in the English meaning of these words. And the additional restrictions that are that age is greater than or equal to 0 and that no one can have more than one spouse. In addition, besides the person class, create a location class, and the properties that have location in the domain will be description, latitude, and the values of latitude can range from minus 90 to 90 inclusive, and longitude, and the values of longitude can range from minus 180 to 180 inclusive. If I didn't explicitly say it, these properties have person in their domain. And finally, create a birth class. And it's in the birth is a domain of the properties mother, baby, date, and location. And add the restriction that an instance of the birth class can have exactly one mother and greater than or equal to one baby. We will begin our solution by creating a new file, which we will call genealogy. And we'll give it a URI as required. So let's start off with our person class. Person is a class. And we'll say that it's described by gender with values of type gender. So I immediately get an error because gender isn't defined. So I can use a quick fix to define it, but I want to define gender a little more specifically. Let's say that it must be one of male, female. And let's extend our definition of person. Let's say that it's described by date of birth with values of type date. We could restrict the number of values, but we won't bother at this point. Described by age with values of type, and let's make that a non-negative integer. And finally, let's say it's described by parent with values of type person. So that gives us a definition for the parent class, or for the person class. Now let's define man and woman, and let's define them with necessary and sufficient conditions. So let's say that a person is a woman. We can say only if, or if and only if. Gender always has value female. And a person is a man if and only if gender always has value male. So adding our additional properties here, we have child describes person with values of type person. Spouse describes person with values of type person. And we had a restriction we wanted to capture, that spouse of person has at most one value. So it might not have any values, but if it has a value, it can't have more than one value. And finally, let's describe sibling. Describes person with values of type person. And we had some additional subclasses. We'll say that a man is a husband only if spouse has at least one value. And a woman is a wife only if spouse has at least one value. And that a person is a parent only if child has at least one value. So that defines husband, wife, and parent in terms of equivalence with a property restriction. We want to define location, and we need to give it some values. So we're going to create a lat value is a type of double, and it's going to be in the range minus 90 to 90 inclusive. And longe value is a type of double, and we're going to put it in the range of a minus 180 to 180 inclusive. So now that we have defined these user-defined data types that are subclasses of double, if you will, or subdata types of double, we'll define location as a class, and it's going to be described by latitude with values of type, and we're going to pick lat value. And it will further be described by longitude with values of type, and here we want longe value. And we said it could also be described by a string description. And I'm missing a by here. Missing by at latitude. So that gives me the location class. And now I'm ready to define the last class, birth. Birth is a class, and it's going to be described by, and we'll use the property mother with a single value of type woman. And we'll say that it's described by baby with values of type person. There can be more than one baby. Might be twins or triplets. Described by date with values of type date. And described by location. With values of type location. Let's see here. What are we doing wrong? We're missing A, which is why the content assist wasn't happy. And finally, we have a restriction that baby of birth has at least one value. We could make it qualified cardinality, but we've already said that baby's range is person, so we're not really further restricting it. And so that gives us our genealogy model, at least one plausible solution, therefore. Let's discuss this possible solution a little bit more and talk about how each of these underlying definitions is realized. So, defining the subclass. So let's look at how man is defined. Where is man? Here we go. A person is a man only if gender always has value female, similar to the way that we defined the class woman. We define man in terms of necessary and sufficient conditions. Man, woman, necessary and sufficient conditions. In terms of has value restrictions on the gender property. So next, let's talk about husband and wife and parent. So a man, we're starting with what was defined by this always has value restriction in necessary and sufficient conditions. So we start with man. A man is a husband only if spouse has at least one value. So this is just the straight minimum cardinality restriction placed on man in order to qualify to be a husband. A woman is a wife only if spouse has at least one value. That's very, very much a parallel definition in terms of a simple minimum cardinality restriction. A person is a parent only if child has at least one value. Once again, we are putting a necessary and sufficient condition on person that child has a minimum cardinality of 1 in order to qualify to be a parent. All three necessary and sufficient conditions. So we said we'd have an additional restriction that age is greater than or equal to 0. Let's see how we achieved that. Where did we achieve that at? Maybe we didn't achieve that. Yes, we did. Here we go. We said that person is described by age with values of type non-negative integer. So a non-negative integer is greater than or equal to 0. So that range puts in the restriction on age. We said no more than one spouse. So we're spouse, here we go. Spouse of person has at most one value. So this is putting a max cardinality restriction for the spouse property on the person class, and that achieves this condition. Let's look at latitude and longitude. So to accomplish this, we define some user-defined data types. And the way we do this in our controlled English, we say here that a lat value is a type of double, and we add a facet that it's in the range, and the square brackets indicate that the range is inclusive of the end values of minus 90.0 plus 90.0. So that is a user-defined data type lat value, and then we give latitude the range lat values. So all values of latitude have to come from this range, doubles in the range of minus 90 to plus 90 inclusive. We do the same kind of thing for longe value, for longitudinal value, except here the inclusive range is minus 180 to 180, and again we just use it as the range. And finally, for the birth class, we wanted the restrictions that there would be exactly one mother and one or more babies. So we said that that baby of birth has at least one value. That handles the greater than or equal. And notice here that we said birth is described by mother with a single value of type woman, instead of saying with values of type. With values of type, we're just specifying the range of the property. But when we say with a single value of type woman, we are putting on a restriction that it can have, that it must have exactly one value of type woman on the birth class. So that completes our additional explanation of the restrictions in our genealogy model.